Hi everyone, this is Mrs. G.A. and today we're going to be doing trapezoidal approximation for area under a curve. So earlier this year, you'll remember that we used rectangles to approximate the area under the curve, and we used Riemann sums to do this. So we did 3 different types of rectangle approximation. We did a left endpoint approximation, a right endpoint approximation, and then a midpoint approximation. But again, this is an approximation for the area under the curve. You can clearly see that sometimes it's a pretty significant underestimate or overestimate. So obviously we know how to calculate a definite integral now, so that is exact, but we're going to talk about a new way to do an approximation. So now, instead of using rectangles, we're going to use trapezoids to help us approximate the area. And you can see that with the trapezoids, it's going to end up being a little bit more accurate than with our rectangles. So we're still going to be dividing our curve up into subintervals. And then we will use the height of our curve to help us dictate different dimensions of our trapezoids. But this time, so our trapezoids are actually going to be kind of vertical trapezoids. So here's the general area of a trapezoid. We know that it's 1/2 times the sum of the two bases times the height. So for us, when we draw these, the height is actually going to be this distance, the distance of each interval. So this is going to be the height, and then we can call this B1 and B2, the sum of the two bases. So our trapezoids are going to be more vertical rather than horizontal like this. And then, sometimes we're going to have equal subintervals, just like with our rectangles, and sometimes, depending on the data we have, each height is going to be different, so we have to calculate them individually. All right, let's try one of these together. So we're going to approximate the area for the definite integral using trapezoids with 3 equal subintervals for this integral. So from 0 to 3 of 4 minus x squared. So let's do a quick sketch. Here's our curve from 0 to 3. So our trapezoids would look something like this. If we have 3 subintervals and it's 0 to 3, each interval is 1 unit. Remember, this is actually going to be considered the height of our trapezoid. And then the first base here will be dictated by this height at the curve, whatever this y value is. And our second base is when the curve, the value for f of 1, and then it would look something like this. So you can see that it's only a slight underestimate here. For our second trapezoid, it actually ends up looking, it's actually more of a triangle than a trapezoid. But we'll still use our trapezoid formula, and then our third one would look like this. All right, so now let's set up the general formula for the area of each of those individual trapezoids. So we're going to do 1/2 times the height. So the height of each of these is going to be 1. So times 1 times the sum of the two bases. So for our first one, this base is going to actually be whatever f of 0 is. And our second base is f of 1. So it's f of 0 plus f of 1. And for our second trapezoid, it's going to be 1/2 times the height of 1. And then our first base is f of 1, and our second base is f of 2. So the sum of f of 1 and f of 2. And then for the third one, 1/2 times 1, and then our first base is f of 2, and our last base is f of 3. So you'll notice here that we can kind of simplify this formula a little bit before we even plug in numbers. All of our trapezoids have a consistent height, so it's going to be 1/2 times 1, and then we can just combine all of the sums. So you'll see that f of 0 is only added once, but f of 1 is actually added twice, f of 2 is added twice, and then f of 3 is only added once. So the ones on your ends are only added once, but all of the other ones will be added twice because they're a base for 2 separate trapezoids. So we have f of 0 plus 2 times f of 1 plus 2 times f of 2, and then plus f of 3. So then we'll just go and plug in those values. F of 0 is 4, and then 2 times 3, 2 times 0, and then a single -5. And then we just simplify from there, and we should end up with 5/2 units squared. So that's our trapezoidal approximation. All right, let's try another one together. So here we have a set of data, and it's from the closed interval 2 to 8, and it has specific values given. So here we want to use the trapezoidal approximation for the integral from 2 to 8 of this function, and we want 3 subintervals. But for this one, you'll notice that the heights of our trapezoids are not consistent, which would be the distance between your x values. So remember, we can't make up data. We have to use the data that's given. So if we are going to use this data, this is our first subinterval. So this height is going to be 3. Here's our second one. This height is going to be 2. And then this height is going to be 1. So to find this area, we have to find the individual areas separately. So for the first trapezoid, it's 1/2 times 3, and then it's going to be f of 2 plus f of 5, so 10 plus 30. This is the height of my 2 bases. And then for the next one, it's 1/2 times 2, and then f of 5 plus f of 7, so 30 plus 40. And then for the last one, 1/2 times 1 times 40 plus 20. And then from here, we can calculate those individually. They are all being multiplied by 1/2, so we can save ourselves a little bit of time there. 120 plus 140 plus 60. So 1/2 times 320 gives us 160. So just be careful if you're working with a table of data. You really need to look at the intervals of your x values, and if it's not an equal subinterval, you do need to do each trapezoid separately. All right, let's try one more together. So this says an experiment was performed in which oxygen was produced at a continuous rate. The rate at which the oxygen was produced was measured each minute, and the results are tabulated here. Use the trapezoidal rule with 3 subintervals indicated by the data in the table to estimate the total amount of oxygen produced in 6 minutes. So remember, if your function is a rate, the integral of that function gives you an amount or a distance. So if we want to find the total amount, it would be the integral from 0 to 6 of whatever this function is. I'll call it f of x dx. So another thing to notice, again, these subintervals are not consistent. This one will have a height of 1, this one will have a height of 2, and this one will have a height of 3. So just be careful with that. And then we'll plug in our values. So our area is going to be 1/2 times 1. And again, this is our first base. This is our second base. So 0 plus 148. That's our first trapezoid. And then 1/2 times 2 times 148 plus 2.2. And then 1/2 times 3, this height. And then those are our 2 bases. So 2.2 plus 3.6. And then here we're just simplifying, and we should end up with 232.9, and then this is just going to be cubic feet. That's the total amount of oxygen produced, so cubic feet of O2 if we want to add. And there you go. So this is just a good reminder that, again, if you have a function that represents the rate of something, the integral would be the amount or the distance. So be careful with your units as well. All right, and last thing really quick, this is just to generalize a trapezoidal rule. Now this rule we can only use if the width of our trapezoids is the same, like it was in the first example, but oftentimes it's not, so just be careful. But it's just 1/2 times the width of each subinterval, so b minus a over n, the number of trapezoids, which again is the height, And then remember, in that first example, your first base was only counted once, your last base was only counted once, but then every other base in between was counted twice because it was part of two trapezoids. So this is the general trapezoidal rule, but again, it can only be used if you have that consistent width. Otherwise, you just calculate them individually by hand. All right, so that is all for today's video. Thank you so much for watching.